Can we do everything? I'm sorry.
No, no problem. Yeah. You cannot minimize Zoom while you are recording this meeting. Okay. So let's see. Can you all see my screen?
No.
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 Okay, let me do a share screen then. So share screen. Advanced portion of the screen. Okay.
Oh goodness.
Can you all see the
I'm
screen
working.
now?
Yes.
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 So yeah, let's go through this thing together. Okay, so the first question starts out by asking which of the following are valid probabilities. Okay, and we remember that for a valid probability, that what you need to have happen is that the probability has to be between 0 and 1. The smallest the probability can ever be is 0. The most it can ever be is 1. Okay. Now they throw a couple curveballs at us where they show things like 83%. Well, if you have a percent, remember that percentage would be like 0.83, and 0.83 would be between 0 and 1. So something like an 83% could represent a valid probability. For A, that wouldn't work because it's negative. You can never be less than 0. B wouldn't work because it's more than 1, so that's out. 0.32%, if you change it to a decimal, that would be 0.0032. So that's between 0 and 1, so that would be valid. D can't work because that's more than 1. And then for E, again, 27%, if we change that to 0.27, that is between 0 and 1, so that one would be valid as well. Does everybody understand that condition for probability?
Mhm.
Has to be between 0 and 1.
Yeah.
The next thing we'll look at is finding the set of all outcomes. So if you have an example 2, you have a regular 6-sided die is rolled, and let A be the event of rolling an odd number. The event A is a set. It just consists of all of the outcomes that would be in A. Well, on a die, you have 1, 3, and 5. Those would be your odd numbers. And then the complement of A would be everything in the sample space except what belongs to A. So if you think of the entire die, it'd be 1, 2, 3, 4, 5, 6. If you remove the 1, the 3, and the 5, what's left over, we call that A complement, and that would be the 2, the 4, and the 6. Just kind of thinking of it, the complement of A is the not A event. So if we did not roll an odd number, then that means that we must have rolled an even. And then, of course, the sample space S just consists of all of the numbers from 1 through 6. 3 and 4 especially, pay close attention to these. I think these are some of the multiple choice ones that kind of often get missed on the test. It's really just a matter of definitions. Independent events, so kind of like the intuitive idea here is 2 events are independent if the occurrence of one event doesn't affect the occurrence of a second event. So with the definition of independent events, it's good to have an example. In class, I talked about either rolling a die and flipping a coin, how whatever happens on the coin isn't going to impact the die, or you can look at selection with replacement. If you do some selection with replacement, if you pick an item and you put it back in the pile, then the second selection isn't going to be dependent on any way what happens in the first. So those would be examples of independent events. For dependent events, that's where the first event will impact the probability of the second event. So think of things like selection without replacement. If I pull one card out of a deck of cards, and then I try to go ahead and choose a second card, because I've removed one card from the deck, that's going to affect the probability of my second pick. In example 3, they say, well, what happens if you roll a 6 on the first die, and then we're looking at rolling a 6 on the second die? Well, those 2 events would be independent, because no matter what happens for the first roll, it's not in any way, shape, or form going to impact or affect what happens when you roll the die a second time. So because those 2 events aren't going to impact each other's probability, we would call those 2 events independent. Does that make sense?
Mm-hmm.
Yeah.
Yeah.
The next one, you gotta be really careful, especially the way this is worded, is the definition of mutually exclusive. We say that two events are mutually exclusive if they can not happen at the same time. Okay, so for example, if we go back to this event here, if you look at the event of rolling an odd number and then the event of, let's say, rolling like an even number, those two events would be mutually exclusive because they cannot happen at the same time. If we look at example 4, the event of scoring a 97 on the test, and then if event B is that of scoring less than an 80, those two would be mutually exclusive because you can't get both a 97 and less than an 80 on at the same time. So they would be mutually exclusive. If the events could happen at the same time, then we would say that the events are not mutually exclusive. For example, if you were to pick a college student at random, if you look at the event A is the event of picking a female, and event B is that of picking a physics major, those two events would not be mutually exclusive because you could pick an individual that's a female physics major, and then both event A and event B would happen at the same time, which means that in that case they would not be mutually exclusive. So just be very careful in the definition of mutually exclusive. It's already kind of a negatively worded phrases. To be mutually exclusive means they can't happen at the same time. Does that make sense?
Yeah.
Okay. In example 5, we kind of come to the designation of data as being discrete or continuous. In this entire chapter, so in chapter 3 and chapter 4, we were working with discrete probability distributions. One of the things you'll see after the test is that when we move on to chapter 5, we're going to begin to focus on continuous random variables. But for right now, everything in this chapter was discrete, and discrete data is just the ones you can count, using nice whole numbers. So the number of dogs in a park at a given time, it'd be either 10 dogs or 12 dogs, etc. But that would be discrete. The amount of time a dog spends in a park on a given day, so if it's time, that can get into fractional values. So if you can measure it to decimal level precision, then that's what makes it continuous. Okay. So a lot of like human characteristics and physical quantities tend to be continuous. Things like time, height, weight, volumes, measurements like lengths, distances. Those are all examples of continuous data because you can have fractions of units. The number of students who answer this question correctly, it would be either exactly 20 or 30, etc. Has to be a whole number, so that would make that discrete data. Any questions on the difference between discrete or continuous?
No.
Let's take a look at number 6 then. Okay. So in number 6, they give us this table, and they simply ask the question, is this a valid probability distribution or not? And the part about this that's very important is we have to know what that means. To be a valid probability distribution means that there's two properties we have to satisfy. The first property is that for every probability, it has to be a true probability, meaning each p of x value has to be between 0 and 1. And then the second important characteristic is that if we add up or sum all of the probabilities, they have to equal out to exactly 1. So let's go ahead and check this. Just a quick glance, I can look at all of these p of x values, and certainly they are between 0 and 1, so that property works. But then the next thing we would have to do is add them all up, and if you do that, they actually add up to 1.3, which isn't 1. So because of that, we would say that no, this is not a valid probability distribution because both properties were not satisfied. Does that make sense? You will see something similar to this later today. Please make sure you know these two properties for a probability distribution. P of x has to be between 0 and 1 for all probabilities. And if you add them up, it has to total up to exactly 1. We come to is example 7. here we have an experiment that consists of tossing a coin and simultaneously rolling a die. The first question just simply says, what is the sample space for this? And it's a sample space, so it's going to be a set, and it's going to be the set of all outcomes. For this experiment, we have two observations to make. We have to observe what the coin shows and simultaneously what the die shows. And really quickly, we would realize that, okay, we could have the coin could show a head. And in addition to that, the die could show any one of the numbers 1 through 6. So we could have like a head with a 1, a head with a 2, a head with a 3, up to a head with a 6. Similarly, if a coin showed a tail, we could have a tail with a 1, a tail with a 2, all the way up to a tail with a 6. So this would be our sample space. It's this collection of outcomes, it's this set. If they asked how many total outcomes are there, we could simply count how many elements are in our set. There would be 12 total outcomes here altogether. If we didn't create the sample space first, we could still tell the total number of outcomes by using that fundamental counting principle. It's the number of ways you can do the first step times the number of ways you can do the second step. There's 2 choices for the coin, 6 choices for the die, so we'd have a total of 2 times 6, which would be 12 possible outcomes for this experiment. Any questions on that part? Is everybody good with 7?
Yeah.
Take a look at number 8. You can definitely tell this review sheet's kind of showing its age. We got an Xbox 360 and a PlayStation 3. They say that in a survey of college students, 827 preferred the Xbox and 673 say they prefer the PlayStation. If we choose one college student at random, find the probability that they prefer the Xbox. This is kind of like your classical model of probability. It's the total number of successes or the total number of elements in the event divided by the total size of the sample space or divided by the total number of individuals. We had 827 people said they prefer the Xbox, so that's going to be our numerator. And the total we had altogether would be found by adding the 827 and the 673, excuse me. So you're going to get 827 over 1,500 for a probability of about 0.551. And this is what we call the classical model. It's just the number of outcomes in your event divided by the total size of the sample space. Let's take a look at number 9. This is, I think, a Star Trek reference. So we have 3 different civilizations that had a certain number of attacks that were made. In part A, it says if one attack from the table is randomly selected, find the probability that it was against the Klingons. So the Klingons, that would be this first row, of which there was 1,063. So we know the number of elements in that event. As we saw in example 8, we would need to divide that by the total number altogether. So we're going to have to sum these all up. Add 1,063 plus 772 plus 665, and that would give us a total of 2,500. So we just take our 1,063 divided by 2,500, and we would get 0.425. In part B, it says find the probability that the attack was not against the Romulans. And there's 2 ways you can do this. You can use the direct approach, which would be to say, okay, let me go up to this table, and I'm going to add all of the non-Romulan attacks. So we could take the Klingons and the Cardassians, add those 2 together, because they're non-Romulans, divide that by the total, that would give us our answer. Okay. Or another approach is we could simply go ahead and use the rule of the complement. If it's not against the Romulans, that would be 1 minus the probability that it would be against the Romulans. So we could do 1 minus, that's going to be 772 over, I made a mistake here. That's not right. The denominator was what? 2,500. So that should have been 1 minus 772 divided by 2,500. And that would give us a total of 0.6912. 0.6912. Does anybody have any questions on part B?
No.
The next one we have is problem number 10. And this is a good one because we have kind of like a stratified table here. Give me 1 second. I think we have some more people that are going to join us.
Question number 9 was also classical, right?
Yes, it
Classical
was.
model.
It absolutely was.
So pretty much with the classical model, what we do is we take our number of outcome and divide by total. We don't have to think much about like, okay, which one to choose.
That's exactly correct. Yep, it's just the total number of events in your sample space, in your event, divided by the size of the sample space.
Okay.
Let's take a look at this one. So our stratified table, we have, according to class ranking, so we have freshman and sophomore are the rows, and then the columns are whether or not these individuals carry credit cards. We see that all together, there's gonna be a total of 100 people. And the first part says, find the probability that the student does not carry a credit card. Well, the probability of no card, all together, that's this column sum. There's 27 individuals that don't carry a credit card out of 100. So that'd be 27 out of 100 or 0.27. In the next part, find the probability that a person is a sophomore given that they do not carry a card. Okay. Now this is what you kind of have to be very careful with and on the lookout for is these key buzzwords. When you hear the word given, that makes it a conditional probability. So we're trying to compute the probability of a sophomore given that they do not have a card. And the way the conditional probability affects things is when they say given that they don't carry a card, instead of looking at the entire population, we know that we can restrict our attention to just this subset. We already know that the person that was selected was one of these 27 individuals that do not carry a card. Now, out of those 27 individuals, the probability that we picked a sophomore, well, there were 6 sophomores out of those 27, would have a probability of 6 over 27, which would be 0.222.
So I have a question on this one.
Yes.
I always confuse myself. I know I have to take 6 for that because it doesn't carry a credit card and a sophomore. But with 27, is it just because it's given they don't carry credit card? Why not I can't take 63? Because it's a sophomore.
Oh, yeah, it's the difference of if you're given, so I think what you would be referring to would be if you're trying to compute the probability of no card given that they're a sophomore. Here, the thing that we know that they have no card. We don't know that they're a sophomore. So we're trying to figure out what are those odds, what's that probability? So when they say, okay, the person you have, given they don't carry a card, that means that it was one of these 27 people.
When he says given, that's what you know. So that's the column or the line that you stay in.
That's the one that you stay in. Yep. So you stay in that column.
No.
And then for that part, what you would look for is, okay, those sophomore.
Oh, no.
6 over 27. And that 6 over 27 would give us 0.222.
No.
The reason why we wouldn't need to look at the 63 is if you look at those 63, that would be the sophomores. And those 63 sophomores would actually include credit card carriers. So the credit card carriers, you know, we know we don't have one of those individuals, so we don't need to consider those people. It'd be only this column. Does that make sense?
So how about if that question would have said, find the probability that they does not carry a credit card given that they are a sophomore, still it would be same?
No, then it would be, so if you flip it around, so if you ask this question now, So if the question then becomes, find the probability of a no card
Mm-hmm.
given sophomore. Now, we know we have a sophomore. So the amount of people we're looking at isn't going to be out of the total. It's going to be out of the sophomores. So if we look at the sophomores, let's go back a minute. How many were there? So 63?
Yes.
There's 63 sophomores. And of those 63, so now you'd be focusing your attention on this group right here. So now we're working out of one of the 63. And out of the 63, there's 6 of them that do not carry a card. So that would be 6 over 63. It would totally change it. So once you know what the given information is, so that's just the notation, it would look like this. That total number is going to be your denominator. So it's not going to be out of the full sample space. It'd be out of just that grouping, which goes down here. And then you would want to see, okay, well, from that grouping, how many of them have that category? And it was 6 sophomores with no card. And that's how we get the probability of 63. Let's take a look at part C. In part C, it says, find the probability that the person is a freshman and does not carry a card. So we're no longer told given anything. So we're now back to the full sample space of 100. And we want to find the probability of a person having both of these traits. So first of all, they should be a freshman, which means they have to belong to this row. And we need them to have a credit card. Excuse me, do not have a credit card. So that means that they also have to belong to this column. And that common intersection is going to be the 21 individuals. These 21 people are both freshmen and do not have a card. So that would give us 21 over 100, which would be 0.210. Let's take a look at the next one. In number 11, this is going to be our multiplication rule. It says a sample of 350 people, 97 people have blue eyes. We're going to pick 2 people at random, and very important, this selection is going to be done without replacement. Find the probability that neither person has blue eyes. So one of the things that we know is that, okay, we have 350 people. If 97 have blue eyes, then 350 minus 97, or the remaining 253, would not have blue eyes. So if we're going to have 2 selections without replacement, the probability of getting the first person that doesn't have blue eyes means it would have to be one of these 253 out of 350. That's the probability of the first event. We now need to multiply that by the probability of the second event, given that the first event has occurred. Well, if we're doing this without replacement, then once we pick somebody, we now have 349 people left to choose for our second pick. And of those 349, if we got a non-blue-eyed person in the first selection, then we have 1 less, meaning we have 252 of those left for the second pick. And we would just simply multiply those 2 probabilities together. And that would give us 0.522.
So instead of 2%, if it would have asked like 3 or 4, we just go, right?
If you had to pick like 3 people?
Yeah, it says 3 people are chosen, so.
So if you had 3 people, then for the next pick, you'd have another fraction here. For the third selection, you'd be down to 251 up top, and you would be down to 348 on the bottom. Good question. Does anybody have any other questions on 11?
And that was multiplication rule.
That's the multiplication rule, yep. If you want to look at the notation, so the notation for that in the notes would be the following. So this is an and probability, but it's a probability of 2 events in sequence. We said that the probability of A and B, this is the probability of the first event, and then you multiply it by the probability of the second event, given that the first event has occurred. We also saw that if A and B are independent, then this formula simplifies
Yeah.
to P of A and B. It's an ugly D. There we go. This is simply going to be P of A times P of B in that case. And the reason for that is if they're independent, then this conditional probability can be replaced with just P of B.
Mm. And the one we have was dependent. That's the reason we chose that.
Exactly right. Because anytime you do selection without replacement, that will always produce dependent events. Let's take a look at number 12. The probability that a person in the US has type O plus blood is 40%. We're going to choose 4 unrelated people at random, and we want to find the probability that none of them have type O plus blood. So right from the start, they tell us the probability of O plus, but we were looking for the probability that none of the 4 have O plus. So one of the things that we're going to need to know is what's the probability that a single person would not have O plus? That would be the complement. So the probability of not O plus would be 1 minus the probability of O plus. That's going to be 1 minus, well, the probability of O plus, if it's 40%, that's 0.40. So for not O, it would be 0.60. And that intuitively should make sense to us, right? If 40% do have it, then that means that the remaining 60% would not have it. Okay. So now the probability of none in this case, okay, that's none out of 4. So we don't need the first person to have it, and the second person shouldn't have it, and the third shouldn't have it, and the fourth person can't have it. Now, because these people are going to be unrelated, these events are going to be independent events. And what that means to us is we can simply just take the probability of each event and multiply them all together. If the first person did not have it, that's 0.6. Second person's 0.6. Third person's 0.6. And then the last person would also be 0.6. If we multiply them all together, we would get a total of 0.130.
So if you happen to change in these questions, like how can you make it a different question?
I mean, I could have reworded it. I could have said, what's the probability that all 4 do have O plus?
Mm-hmm.
In which case these would all be 0.4s.
Mm-hmm.
I wouldn't do an at least 1 on this, although I could as a follow-up, because we know that at least 1 is 1 minus probability of none. But it would probably stick kind of close to this. This is just an example of an extended multiplication rule. So in terms of like the test, if you're kind of asking, you know, just kind of read it very critically, because the 2 variations of this could be the probability that none of them have O plus, or I could have even said what's the probability that all of them do have O plus.
So if all, then we just multiply by 0.4.
Correct.
And at least 1 is 1 negative whatever this 1.30.
Correct.
Okay.
Can I ask a question?
Yeah, absolutely. What you got?
So I just have, looking back on the notes, I've just had a hard time picking which formula to like put with the problem. I did this problem the way you just said, and I did it with a binomial like PDF, and it worked as well. Is that just like happenstance? Like,
No. So you're absolutely correct about that. So
like would I've gotten credit for that work?
you absolutely would have, because even though we hadn't quite, so when this was introduced way back in chapter 3. This actually is a binomial process, because if you pick an individual at random, there's 2 outcomes. Either they do or do not have O plus blood. So you could label 1 a success, label 1 a failure. And then because the events are independent, that would absolutely make this a binomial process. So yeah, if you solve this with binomial PDF, that's perfectly valid too.
Okay, thank you.
Yep, absolutely. Let's take a look at the next one. So again, buzzwords are key here. So if you hear things like and, or an or a given, that lends us to a certain type of computation for the probability. In this example, we're asked to compute the probability the person is a woman or an astrophysics major. So when you hear that buzzword, the probability of something or something, that's going to lead us to what we call the addition rule. Okay. So as a reminder, what the addition rule says is the following. If you want to calculate the probability of A or B, this is the probability of A plus the probability of B minus the probability of A and B. If the events happen to be mutually exclusive, then this formula would simplify a little bit. And if the two events are mutually exclusive, then that means that they cannot happen at the same time, which would mean that that last term would be 0. But this would be the general addition rule. And because we have an OR probability, we're going to use this rule. So the probability of a woman or an astrophysics major would be the probability of a woman plus the probability of an astrophysics major minus the probability of a woman that is also an astrophysics major. We're going to have a little bit of work to do to kind of figure out each of these pieces. So first thing, we know that there's 3,500 people altogether. Now, they don't tell us the females, but they do tell us that there's 2,200 men. So we can find the number of women by simply subtracting the 3,500 from 2,200, and that would give us 1,300 women. The next thing we have would be the probability of an astrophysics major. And we know that altogether there's 970 astrophysics majors there. So the probability of an astrophysics major would be 970 divided by 3,500. And now we need to subtract by the probability of a woman astrophysics major. And they tell us up front that there's 360 of those. So that's 360 over 3,500. If you just plug it into your calculator, do all these fractions, you should get a probability of 0.546. 0.546. Does anybody have any questions on number 13? Let's take a look at 14 then. So here we have our deck of cards. It says a card is selected at random from the standard deck. Find the probability of selecting a heart and a face card. So we're picking one card, and we need for that card to be both a heart and, in addition, it must be a face card, meaning it has to be either the jack, the queen, or the king. And in the deck, there's only 3 such cards. You have the jack of hearts and the king of hearts. So that's 3 out of 52 cards for a probability of 0.058. So for this one, there's really nothing fancy you have to do. You can just simply count the number of outcomes and divide it by the size of the sample space. Are there any questions on 14 or card questions in general?
Could you go back up to 13 real fast so I could see the last part of the problem?
Absolutely.
Thank you. When I was doing it, I was trying to get like all the decimal places first, so it just looked like more work on my paper.
Yeah, that can certainly happen. I mean, if you're using your calculator, what I would probably do is I just plug it in like one computation. I would do like 1,300 divided by 3,500, and I just keep entering the whole thing. Plus 970 divided by 3,500, and then I have a minus 360 divided by 3,500. And this would save you from having to like mess around like the in-between decimals. And so the 3 places you get your 0.546.
Yeah,
While we're on
that's
the
what,
topic, go ahead, sorry.
no. I was just gonna say that's what I was doing. My bad.
Oh, no worries.
All right, while we're on the topic of decimals,
Yes.
that has been my biggest problem, especially through the last section, section 4.2, is like, I mean, I had one in particular problem that I know I probably worked on for half an hour, 45 minutes, just because my decimal, I guess I didn't take my decimals either far enough or too far or whatever. And because the program only gives us credit for, I think it's 0.001, either one way or the other.
Yeah.
Like, I mean, I had the right answer, but I was off by 1,000th or whatever. And literally, and that's my concern with the test, is if it took me that long to do one problem because of decimals, like that's my concern, that I'm going to run out of time taking the test because I'm not going to have the correct, I'm going to have to keep doing the work over and over again to get the right decimal.
Yeah, so that's a very good question. In terms of the test, so like, I'm going to be much more forgiving than what my stat lab is. I mean, they want it to, accurately to like, the 1,000th place a lot of times, or at least, 3 decimal places. For me, as long as you're accurate within reason, like if I say round to 3 places, but you round it to 2 by accident, or if your third place is off by 1 or 2. I'm not gonna knock you for that. But it does bring a good point. And one of the things that happens for accuracy, let's talk about this, is if I have a problem, right? And let's suppose I have I want my answer rounded to 3 decimal places. If I have like a bunch of computations, and if I start rounding to 3 decimal places when I'm doing like operations and stuff, then what happens is every time you use a rounded number in an operation, it compounds the rounding error. So it's always best if you're working out a problem to only ever round one time, and that would be at the very, very, very end. Now, sometimes you can get away with this. Like, for example, if I was doing 3 decimal places, if I'm going to do rounding, it's a good idea to take the between places a little bit. So, like, go at least to like 5 places, and then at least if you go to 5 places, then that third place should be affected, and it should still give you the accurate answer.
Hope. No.
Does that make sense?
Yeah,
Okay.
I think it does. When you're doing
But in
like,
general, I'll be pretty forgiving on the test. You know, all
like-
of the problems say to round to either 2 or 3 places, and as long as you're close enough so that I know you know what you're doing, you'll get full credit.
or if we show our work.
Yes, and show you.
I mean,
work
like,
too.
Because like, okay, in 4.2, when we had, where we were adding together 1, 2, 3, 5 or 6 of the things with the C in it,
Yes.
and you went to 4 or 5 places in all of them, like I was off by 0.008
Oh wow.
because I cut it because I only went 4 places instead of like, because the calculator was giving you like 6 and 7 places. So I was like, okay, well 4 or 5 should be sufficient. Clearly it was not.
Yeah, if you go to 4, it could potentially mess up.
Yeah, it did.
But if you went to 5, I think you would have been fine with 5, unfortunately. If that happens, just email me. I can look at it. So if you're off by just a little bit, that's good enough for me. I know that you know what you're doing there. And that'll save you from having to redo the whole problem. I can manually go in, look at your answer, and say, yep, you were close enough. I knew you know what you're doing. And then any difference would just due to round off error.
Okay.
Yeah, but in general, that should help. Only ever round at the end. Or if you are going to use a rounded answer in a problem, take it out to at least 2 or 3 more places than what the final answer is asking for.
You know that because it's supposed to go 1 more than what your number was it was asking for, right?
Exactly. Let's take a look at 15. So 15, we're kind of back to another stratified table. Here, the stratification is based upon gender, man or woman. And then we have also based upon type of athletic routine, whether it's aerobic, anaerobic, or a combination. There's 500 people altogether. And the first one says, given that the person is a female, find the probability that the primary routine is aerobic. And the key word here is the word given. So this is a conditional probability. So we're given, and we know that we have a female individual. So that means that we can restrict our attention to just this second row. So the person that was selected is one of these 245 individuals. So our denominator for this is going to be 245. Of those 245, how many of them had an aerobic routine? Well, out of the 245, it was 180 of them. So the probability of selecting someone that has an aerobic routine, given or knowing ahead of time that they were a female, would be the 180 divided by the 245, and that would be 0.735. In part B, it's an OR probability, the probability of anaerobic or a combo. So that's going to be our addition rule. It'd be the probability of anaerobic plus the probability of combination minus the probability of anaerobic and combination. Anaerobic, if we go up, that's going to be 105 out of the 500 plus the probability of a combination. That's going to be 130 out of the 500. And then the workouts that would be both anaerobic and combination, that would be 0 because those are going to be mutually exclusive. A workout could be either anaerobic or combination, but not both at the same time because they're different categories. So this last term would just be 0, and we would get a probability there of about 0.47 something. Got cut off. So it's what, 235. Should be able to do it in my head. Just multiply by 2, top and bottom, but I haven't had enough coffee this morning for that. Let's see. Oh, yeah, just 0.470. Does anybody have any questions on 15?
If you could just wait a second so I could see it, that would be.
Absolutely.
Thank you.
You're welcome.
So for 15A again, because of that given that, it throws me off. So let's say if it's given that routine is aerobic and then find the probability of female, so it will be flipped, right?
It would be.
So it will be 100.
So if we knew that it was aerobic, then you would be working out of 265. So you would restrict your attention to just the 265 column.
Okay.
And then the probability of a woman given aerobic would be 180 out of 265.
Okay.
Let's take a look at number 16. So now we start to move into our counting examples. We have a pool of 30 individuals, and from those 30 individuals, we need to choose a captain, a first officer, a science officer, and a chief science officer. That is 1, 2, 3, 4. Oh wait, 5 positions? 1, 2, 3. Oh, no, just 4 positions. Sorry. So there's just 4 positions here. Now, because the positions have names, there's some rank associated to them. So there's some order to these. If you were one of these 30 individuals, it would be a different outcome if you were chosen as captain versus if you were chosen as, let's say, like science officer. So because the order matters, this is going to make this a permutation. To do a permutation, you start with the number n. That's how many you have to choose from. Here we have 30 qualified candidates. You would then need to do a permutation because order matters. You go to math, go over to probability, go down to option 2, that's NPR, and then we're choosing 4 individuals. If we hit enter, that's where we get the 657,720 possibilities. So the key here is when order matters, that makes it a permutation. In number 17, it says we're going to make a meal by doing 4 choices amongst 20 options. And we assume that we're not going to be able to make the same choice twice. So for something like this, if you choose, let's suppose like 4 items. Suppose you pick, I don't know, maybe meatloaf, green beans, mac and cheese, and maybe pie. If that's your meal, no matter what order you pick those items on, once you put them on your plate, it's the same meal no matter what order they come. So for this one, order isn't going to matter at all, and that's what's going to make it a combination. So when order does not matter, we have a combination. We start by putting the number we have to choose from. So we have 20 options. I then go to math, over to the probability menu, NCR, that's combination, and we're selecting 4 of them. So from a list of 20 things, if we're choosing 4 of them without replacement and order doesn't matter, it's a combination, and that would be 4,845 possibilities. Let's take a look at the next example. This is now moving into chapter 4. This would be the probability distribution stuff. In number 18, they give us the random variable x is the number of, what is it? The number of class M planets found during certain missions. For example, there were 0 found in 1,730 missions, and that has a probability of 7.12. Where that probability of 7.12 is coming from is you need to take the number of missions, that's the 1,730, and we would need the total for this. So if we add all of these missions up, what we would find is that the total number of missions is 2,430. So the first step is we need to complete this table by filling in the unknown information. Okay. Well, the probability of finding a class 1 planet, planet, that's going to be 277 out of the total. 277 divided by 2,430 would be 0.114. To find the probability of getting 3 such planets, it's the number of times that occurred, that's 106 out of the 2,430. That would give us a probability of 0.044. And then the probability of 4 planets, that's 63 out of our 2,430 missions. And that would happen with probability 0.026. So the first part's pretty straightforward. Just computing a general probability using the frequency approach. It's the frequency of the event divided by the total of all of the frequencies. In the next part, we're asked to find the mean and the standard deviation of the probability distribution. For this, we can use the calculator. This is going to be our 2 lists setup. It's important that you always put the x values in list L1. Our x values were these ones here, 0 through 5. And then directly across from them, we have to put the associated probabilities. So 0.712, 0.114, for 2 it's 0.0918, 0.044, 0.026, and then 0.0128. I'm going to go ahead and hit enter. And then the way that we would do this to calculate the mean and the standard deviation, you would go to the stat button, go over to calculate. We're going to do one variable statistics. And for those of you using the 84, you want the list to be in L1, and we want for the frequency list to have L2 in it. So I would do second 2 to put the L2 in there, and then I can go ahead and put this on the home screen. If you're using a TI-83, then whenever you hit stat and go over to calculate and hit one variable stat, what it would do is put one variable stat on your home screen, and then you would need to put second 1 and comma second 2 so that it looks like one variable stat L1 comma L2 before you hit enter. But what we should find is that for the mean of this, if we look at a calculator, if I can grab the calculator, come here. There we go. So the mean is going to be to 3 places 0.597. And for the standard deviation is going to be 1.121. Does anybody have any questions with finding the mean and standard deviation of a probability distribution using the calculator?
Yeah, sorry, could you just move the calculator for a second?
Yeah, absolutely.
I can't see the end of the problem.
Yeah, let me scroll down because we were working on this piece right there.
Okay, thank you.
You're welcome. The last part of this question is just some standard probabilities. Find the probability of selecting at least 3. Well, at least 3, going back to our table, means 3 or more. So that would include the event of 3, the event of 4, and the event of 5. You would simply take those 3 events, add the probabilities together, and we would find the probability of at least 3 class M planets would be 0.0828. If we wanted to find the probability of fewer than 3 means less than 3. So that would have to include the 0, the 1, and the 2. So one approach would be simply to take P of 0 plus P of 1 plus P of 2. Or you might recognize that the complement of fewer than 3, so if you don't have fewer than 3, then that must mean you could have 3 or more. And that was the answer to the previous part. So you could use the rule of the complement to do 1 minus the previous answer And either way you do it, you're going to get 0.9172. So 0.9172. The last question that's going to be on the test. So on our exam, I believe we only have 19 questions. I combined number 19 and 20 because they're really on the same information anyway. But the last question is going to be our binomial PDF stuff. And in the first one, it's going to be a binomial PDF calculation. The first thing you would want to do, and it's a good idea, is to write out the N, the P, the Q, and also the range for your X values. Here, they tell us that the probability that a single individual will turn to the dark side is 0.07. So that's going to be the probability of a success. That's 0.07. The Q value, that's the probability of failure. That's always 1 minus P. So if you do 1 minus 0.07, that would give us 0.93. This person's going to train 7 apprentices. So the number of trials, N, is 7. And for the random variable, the number of individuals that could turn to the dark side, recall that X always ranges from a minimum of 0 up to the maximum of N. So the random variable X could have any value from 0, 1, 2, 3, 4, all the way up to 7. And then in the first part, they say, well, what is the probability that exactly 2 of them will turn? And we can use our binomial PDF calculation to do this. So if we want the probability of exactly 2 successes, we would go second, distribution. So it's under the distribution menu. It's the second and then the vars key. We're going to scroll down a little ways and be very careful here. There's 2 options that sound similar. There's a binomial PDF and a binomial CDF. The binomial PDF is the one that we're going to use, always choice A. For the TI-84, it kind of prompts you nicely for N, P, and X in that order. We have 7 trials. The probability of success on a single trial is 0.07. And we're looking for exactly 2 successes. So X is going to be 2. If you're doing it with the TI-83, then it's not going to ask you with that previous screen. You don't get that input screen. But you're going to have to just kind of remember that in order, for your binomial PDF, it has to go in the order N, P, and X. And they have to be separated by commas. So you do 7, comma, 0.07, comma, and then 2. We go ahead and hit enter, and we would get 0.072, and that's rounded to 3 places. The other part of this problem that's going to be attached is I'm not going to have you find the entire distribution, so you do not have to find the X values, but I will ask you for the mean, the variance, and the standard deviation. And because this is a binomial probability distribution, we have these shortcut formulas that you're allowed to use on the test. To find the mean for a binomial probability distribution, you simply can just do N times P. N was 7, P was 0.07. We multiply them and we get 0.49. To find the variance, that's sigma squared, you just do N times P times Q. That's 7 times 0.07 times 0.93. That will give us 0.45. I should have rounded it, 0.456, we'll say. And then for the standard deviation is simply the square root of the variance. So it's the square root of N times P times Q. If I do the square root of 0.4557, we would get 0.675. And that will be the last part of that question. You don't have to do the previous part with the distribution. Does anybody have any questions on this 19 or 20?
No, but if we have a second, can we go back to 18?
Absolutely. Yes. What part of 18 would you like to look at?
I got confused. After we have the table with L1 and L2 on part B.
Yes.
what's the next step?
Sure. So after you have that, you're going to hit the stat button. So hit stat right here.
Mm-hmm.
You're going to go over to calculate. And then we're going to do one variable statistics. Hit enter. And then do you have an 83 or 84 calculator?
83.
83. So for you, the next step, once you have that in there, is you need to hit, you need to get the one variable stat on the home screen. And then you would hit second one key. And then you hit the comma second two. Because it should show up as like one variable stat. It should look like this on your home screen. One variable stat with an L1 beside it and a comma L2.
Okay.
Excellent question.